This is Chapter 11, Acids and Bases. Section 3 is Strengths of Acids and Bases. We saw at the beginning of this chapter that acids and bases are really special kinds of electrolytes, substances that dissociate into ions when you dissolve them into water solutions. From the chapter on solutions, you may remember that electrolytes can be either strong or weak depending on how much they dissociate. Fluoride, for example, is the only halogen ion that forms a weak acid with hydrogen. HF is hydrofluoric acid. The other halogens, chlorine, bromine, and iodine, all form strong acids. In this section, we're going to learn about the difference between strong and weak acids and bases, and learn how to write the dissociation reactions between them. When we talk about strong and weak acids, it's in the same sense that we talk about strong and weak electrolytes. So a strong acid, just like a strong electrolyte, will completely ionize or dissociate into ions when you dissolve it into an aqueous solution. The most common example of this is HCl, hydrochloric acid. When you dissolve HCl into water, it separates into chloride ions and hydrogen ions, which then immediately combine with water molecules to form hydronium, H3O+. This reaction goes all the way to the right, it goes to completion, meaning that every molecule of HCl that you dissolve will separate into these ions. There'll be no intact neutral HCl molecules left once the dissociation is complete. A weak acid, on the other hand, only dissociates or ionizes partially when you put it into water. So carbonic acid, for example, can interact with water. It'll separate into bicarbonate ions, and then the hydrogen will form hydronium. But these ions can also reform back into the original carbonic acid molecule. This is an equilibrium reaction, indicated by these arrows here. And so as a result, once this dissociation process is complete and reaches equilibrium, you're going to have some of each of these species present in the solution. This animation will illustrate the difference between strong and weak acids. On the left, we have hydrochloric acid, where the small white circle is a hydrogen ion and the larger green circle is a chloride ion. On the right, we have hydrofluoric acid, where the larger purple circle this time is a fluoride ion. When you dissolve hydrochloric acid into solution, every molecule that you put in completely separates into ions. And you can see the hydrogen ions immediately find a water molecule and form H3O+, the hydronium ion. This means that if we put in 5 moles of hydrochloric acid, we're going to get 5 moles of hydronium ions and 5 moles of chloride. The chloride isn't that important for the acidity of the solution, but the 5 moles of hydronium will really determine how acidic this solution is. For the weak acid, hydrofluoric acid, most of the molecules that you put in stay connected. They stay intact and do not dissociate into ions. Only a small percentage of them will. In this illustration, we've seen that about 1 in 5 molecules of HF will separate into ions. That means that for every 5 moles of hydrofluoric acid that we dissolve, we'll only end up with 1 mole of hydronium and 1 mole of fluoride and 4 moles of HF, but again, the last two things don't really affect the acidity of the solution. The only thing that affects the acidity is the hydronium ion. So we can see that this is a weaker acid because when we put in the same number of moles of acid, we get fewer moles of the hydronium ion. This picture uses a bar chart to illustrate the action of a strong acid in a way similar to how we looked at the way equilibrium works in the previous chapter. Here we're looking at the dissociation of HI, hydroiodic acid, into the individual iodide ions and hydronium ions. Since this is a strong acid, we can start with any amount of HI at the beginning, but once we dissolve it into water, it's going to fully dissociate into hydronium and iodide. There's no more HI left once the dissociation is complete. This produces large concentrations of hydronium for the given amount of acid that's added to the water. For weak acids, only a small amount dissociates. Here we're looking at hydrofluoric acid, which produces fluoride and hydronium. And so if we start with some amount of hydrofluoric acid, after we wait a little while for it to dissolve, it'll still be mostly hydrofluoric acid with only a small amount of hydronium and fluoride ions. This produces small concentrations of hydronium relative to the amount of acid that we put in. This is why it's called a weak acid. This chart shows the relative strengths of some acids and bases, with the acids listed here on the left and their conjugate bases listed here on the right. Now it's important to remember that the strength of an acid is related to how easily the substance gives away a proton. The strength of a base, on the other hand, is related to how easily a substance takes or accepts a proton. If you think about it, that means that the strength of a conjugate base is going to be inversely related to the strength of the acid that it came from. In other words, if it's very easy for hydrochloric acid to give away a proton, it's not going to be very easy for the chloride ion that results to take back a proton. So we see that on the left-hand side, the strongest acids are up here at the top, and the weakest are down here at the bottom. Whereas for the conjugate bases, the order is reversed. The weakest bases are up here at the top, and the strongest bases are down here at the bottom. There's a lot of information in this chart, and we'll see how to use it more a little bit later. But for now, the most important takeaway is to see that there's this list of 6 strong acids up at the top, and that every other acid that's not a part of that list is considered a weak acid. Those strong acids which you should memorize are hydroiodic acid, hydrobromic acid, perchloric acid, hydrochloric acid, sulfuric acid, and nitric acid. The hydronium ion itself is also considered a strong acid, but it really marks the difference between weak acids and strong acids. Anything that is more likely to dissociate than the hydronium ion is considered strong. Anything that's less likely to dissociate is considered weak. If you look for a list of strong acids online, you may find that 1 or 2 of these are slightly different because there are certain edge cases where the strength of an acid is similar to hydronium depending on certain conditions. For our class, this list of 6 strong acids are the ones that you need to remember. Since we're talking about the dissociation of acids, now is also a good time to look at diprotic acids. These are acids that have 2 protons. Di means 2, protic refers to protons, and so these are acids that have 2 H+ ions in them, each of which can dissociate. These dissociations occur one step at a time. So for example, with carbonic acid, which is H2CO3, there are obviously 2 hydrogens here. The first can separate in an equilibrium reaction where it yields HCO3- and hydronium, H3O+. And then the HCO3- still has a hydrogen in it, and so it itself can undergo another dissociation where it becomes carbonate, CO3-2-, and produces a little bit more hydronium. Here you can see illustrations of the structure of the carbonic acid molecule itself. This is one hydrogen, and this is another hydrogen. After the first dissociation step, you can see that it's lost one of those hydrogens, and after the second dissociation step, both hydrogens are gone. Sulfuric acid is another example of a diprotic acid. However, unlike carbonic acid, the first proton dissociation in sulfuric acid is strong. H2SO4 fully dissociates into solution to give you HSO4- and H3O+. After that, the HSO4 undergoes a further dissociation step to produce the sulfate ion, SO4-2-, but this is also a weak acid dissociation. Strong bases, like strong acids, are those that fully dissociate into ions in solution. We saw in the previous section how ammonia can act as a base by accepting a proton from water and leaving behind a hydroxide. But ammonia is a weak base, and most bases that behave that way are actually weak bases. All of the strong bases that we need to know about already contain a hydroxide ion. In fact, it's very easy because these are ionic compounds that fully dissociate, and the positive ions that are most soluble in water are all of the group 1 metals. So lithium, sodium, potassium, rubidium, and cesium are all group 1 metals, and the hydroxides of each of these form the list of strong bases. If we look at the group 2 metals, like magnesium, calcium, strontium, and barium, these can also be considered strong bases under certain conditions. However, you can see this asterisk here, which tells you that these substances, even though they fully dissociate in water, they still have a very low solubility. So you don't get much dissolved in them. They stay mostly insoluble solids. Therefore, the real list of strong bases that you should remember are these. And again, it's just the hydroxides of the group 1 metals, so there's not really too much to remember. Weak bases are any base that doesn't fully dissociate, so anything other than those examples we saw on the previous page. Again, these are weak electrolytes. They partially dissociate, or in the case of something like ammonia, they partially take a proton and leave behind a hydroxide ion. Either way that they do it, they leave behind very few hydroxide ions in solution relative to the amount of base that you add. This means that they're weak hydrogen acceptors. Ammonia is an example of this. And again, when we talk about the ionization of ammonia, we use two-way equilibrium arrows because it's a weak base. For acids, many of the most common examples that we encounter in everyday life are in the foods that we eat. For example, acetic acid in vinegar or the citric acid found in citrus fruits like lemons or limes. For bases, on the other hand, most of the more common examples are in soaps and detergents found throughout your house. So, for example, baking powder, which can be used as a laundry detergent, you have sodium carbonate, and that's a basic salt. Baking soda, which is often found in toothpaste, is a related salt called sodium bicarbonate. Ammonia is often the major component in window cleaner. Bleach is formed from sodium hypochlorite. Lime for your lawn is calcium carbonate, and laxatives or antacids are typically low-soluble hydroxides. Strong bases, on the other hand, are much more powerful cleaning agents that you would use for something like drain cleaner or oven cleaner. Sodium hydroxide is a strong base that would be used for this type of application. In fact, sodium hydroxide and other hydroxides are collectively known as lye and were originally used in the production of soap. So we've seen in previous sections that any acid-base reaction can really be seen as the exchange of a single proton between the two different substances. In the case where you have a strong acid or a strong base, it's usually pretty clear which way the reaction goes. The strong acid will give away all its protons, or a strong base will take all the protons it can find. But most acid-base reactions are somewhere in the middle. They're equilibrium reactions involving weak acids and weak bases. So for these kinds of reactions, an important question that we might want to answer is which way does the reaction go? Which substances do we have more of once this reaction is complete and we've reached equilibrium? In other words, for this example equation here, do we have more HA plus and B at equilibrium, or do we have more A and HB plus at equilibrium? The answer, of course, depends on the strengths of the acids and bases involved. A stronger acid will lose protons more easily. That's the definition of acid strength. The weaker acid will then be more stable with the proton on it. Similarly, a stronger base will attract protons more, and so the weaker base will be the one that's more stable without the proton. At equilibrium, there will be more of the weak acid in the weak base, because the strong acid is more stable as just its conjugate base, and the weak acid is more stable in the acidic form with the hydrogen. We say that the equilibrium favors the weaker acid and base. Let's take a look at this example to see how this works. Here we have H2SO4, which is sulfuric acid, and this is dissolved into water, H2O. And when sulfuric acid interacts with water, it donates a proton, it loses a proton to become HSO4-, and the water gains a proton to become H3O+. So it's clear that sulfuric acid is giving away a proton, which makes it an acid. The water is taking a proton, which makes it a base. On the right-hand side, the HSO4 is the conjugate base to the sulfuric acid, and the H3O+ is the conjugate acid to the original water. So we have to look at the strengths of the sulfuric acid relative to the strength of the hydronium ion to see which direction this reaction will go. From table 11.3, we can see that H3O+ is a weaker acid than H2SO4. H2SO4 is higher up on the list of acids than H3O+. This means that the equilibrium is going to favor the weaker acid, H3O+, and is going to lie mainly to the right. You could also analyze this in terms of the strengths of the bases. If you look at the same table, 11.3, you'll see that H2O is a stronger base because it's lower down in the chart than HSO4-. HSO4- is the weaker base, and so the equilibrium prefers the side of the weaker base, just the way it prefers the side of the weaker acid. Thus, the equilibrium here favors the right-hand side. At equilibrium, there'll be more HSO4- and H3O+, and very little H2O and H2SO4. In fact, since we know that H2SO4 is actually a strong acid, we should know that this reaction will in fact lie all the way to the right, and it'll be completely dissociated. Here's another example where we don't have any strong acids or bases, and so we'll have to look at the strengths of the weak acids and bases. Here we have carbonate, CO3 2- interacting with water, and carbonate has no hydrogens to donate, so it's going to take a hydrogen from water and become bicarbonate, HCO3-. That's going to leave behind a hydroxide ion. So if we look at the acids, we have water behaving as an acid on the left-hand side, and HCO3- behaving as an acid on the right-hand side. We can look at table 11.3 and we find that HCO3- is going to be higher up than H2O, and so HCO3- is the stronger acid. Water is the weaker acid. We can also look at the bases and we find that hydroxide ion is a stronger base than the carbonate ion, CO3 2-. That's because OH- is further down on that table than CO3 2-. That makes CO3 2- the weaker base. Since the weaker acid and the weaker base are both on the left-hand side, this equilibrium is going to favor the reactants. In other words, at equilibrium, you're going to have more carbonate and water than you have bicarbonate and hydroxide. Both of those previous examples looked at what happens when you combine a substance with water. But you can also look at a direct interaction between an acid and a base without considering the water explicitly. All of these reactions still take place in aqueous solutions, but we don't care about what happens with the water because we consider the acid and the base to be directly reacting with one another. So this example is H2SO4, sulfuric acid, combining with CO3 2- carbonate, and this produces HSO4- and HCO3-. Question is, which side of this reaction is preferred at equilibrium? Again, if we look at table 11.3, we can see that HCO3- is a weaker acid than H2SO4, sulfuric acid, and HSO4- is a weaker base than CO3 2-, the carbonate ion. This means that both of the weaker substances are on the right-hand side, and so the equilibrium will prefer the product side. At equilibrium, you'll have more HSO4- and HCO3- than H2SO4 and CO3 2-. In fact, this problem would be even easier if you recognize right away that H2SO4 is one of the strong acids. That means that H2SO4 is going to immediately dissociate in solution, and there'll be no neutral H2SO4 molecules left. All of the protons from H2SO4 will seek out and find bases to protonate. Even if they can't find any bases to protonate, they'll protonate water and form hydronium. So this equilibrium is definitely going to lie all the way to the right, and there'll be no H2SO4 left, and depending on limiting reactants, there may or may not be any carbonate left. It's important to be able to identify an acid or a base as either strong or weak. For now, you may still need to refer to the chart, but eventually you should memorize the list of 6 strong acids as well as the list of strong bases, which really just come from the group 1 metals. So let's take a look at these examples. First, we have HBr. This is a hydrogen-containing compound, and so it's pretty clear that this is an acid. In fact, HBr is one of the strong acids that was listed at the top of that chart. HNO2 also contains a hydrogen ion, and so this is also an acid, but this is a weak acid. Careful not to confuse it with HNO3. HNO3 is nitric acid, and that is one of the strong acids. HNO2 is nitrous acid, and that is a weak acid. The third example, NaOH, is clearly a base because it has hydroxide in it, and sodium is a group 1 metal, which means that this is a strong base. H2SO4 is again clearly an acid because it has hydrogen ions at the beginning, and this is one of the examples of a strong acid. The last example is copper hydroxide, CuOH2. Hydroxide obviously makes this thing a base, but since we're dealing with copper, this is a transition metal. It's not a group 1 metal or even a group 2 metal, and so this is definitely a weak base.